All right, so today I'm going to be talking about the Lagrangian. Now we've talked about Lagrange multipliers. This is a highly related concept. In fact, it's not really teaching anything new. This is just repackaging stuff that we already know. So to remind you of the setup, this is going to be a constrained optimization problem setup. So we'll have some kind of multivariable function, f of x, y. And the one I have pictured here is, let's see, it's x squared times e to the y times y. So what I have shown here is a contour line for this function. So that is, we say what happens if we set this equal to some constant, and we ask about all values of x and y such that this holds, such that this function outputs that constant. And if I choose a different constant, then that contour line could look a little bit different. It's kind of nice that it has similar shapes. So that's the function, and we're trying to maximize it. The goal is to maximize this guy. And of course, it's not just that. The reason we call it a constrained optimization problem is because there's some kind of constraint, some kind of other function, g of x, y, in this case, x squared plus y squared, and we want to say that this has to equal some specific amount. In this case, I'm going to set it equal to 4. So we say you can't look at any xy to maximize this function. You're limited to the values of x and y that satisfy this property. And I talked about this in the last couple videos, and kind of the cool thing that we found was that you look through the various different contour lines of f, and the maximum will be achieved when that contour line is just perfectly parallel to this contour of g. And you know, a pretty classic example for what these sorts of things could mean or how it's used in practice is if this was, say, a revenue function for some kind of company. You're kind of modeling your revenues based on different choices you could make running that company. And the constraint that you'd have would be, let's say, a budget. So I'm just going to go ahead and write budget, or B for budget here. So you're trying to maximize revenues, and then you have some sort of dollar limit for what you're willing to spend. And these, of course, are just kind of made-up functions. You'd never have a budget that looks like a circle and this kind of random configuration for your revenue. But in principle, you know what I mean, right? So the way that we took advantage of this tangency property, and I think this is pretty clever. Let me just kind of redraw it over here. You're looking at the point where the two functions are just tangent to each other, is that the gradient vector for the thing we're maximizing, which in this case is r, is going to be parallel or proportional to the gradient vector of the constraint, which in this case is b. It's going to be proportional to the gradient of the constraint. And what this means is that if we were going to solve a set of equations, what you set up is you compute that gradient of r, and it'll involve, two different partial derivatives, and you set it equal not to the gradient of b, because it's not necessarily equal to the gradient of b, but it's proportional with some kind of proportionality constant lambda. Now that's kind of a squirrely lambda. Yeah, that one doesn't look good either, does it? Why are lambdas so hard to draw? All right, that looks fine. So the gradient of the revenue is proportional to the gradient of the budget. And we did a couple examples of solving this kind of thing. This gives you two separate equations from the two partial derivatives, and then you use this right here, this budget constraint, as your third equation. And the Lagrangian, the point of this video, this Lagrangian function, is basically just a way to package up this equation along with this equation into a single entity. So it's not really adding new information, and if you're solving things by hand, it doesn't really do anything for you. But what makes it nice is that it's something easier to hand a computer, and I'll show you what I mean. So I'm going to define the Lagrangian itself, which we write with this kind of funky-looking script L, and it's a function with the same inputs that your revenue function, or the thing that you're maximizing, has, along with lambda, along with that Lagrange multiplier. And the way that we define it, and I'm going to need some extra room, so I'm going to say it's equal to, and kind of define it down here, the revenue function, or whatever it is that you're maximizing, the function that you're maximizing, minus lambda, that Lagrange multiplier, so that's just another input to this new function that we're defining, multiplied by the constraint function, in this case b, evaluated at xy, minus whatever that constraint value is. In this case, I put in 4, so you'd write minus 4. If we wanted to be more general, maybe we would write, b for whatever your budget is. So over here, you're subtracting off little b. So this here is a new multivariable function, right? It's something where you could input x, y, and lambda and just kind of plug it all in, and you'd get some kind of value. And remember, b in this case is a constant, so I'll go ahead and write that this right here, is not considered a variable. This is just some constant. Your variables are x, y, and lambda. And this would seem like a totally weird and random thing to do if you just saw it out of context or if it was unmotivated. But what's kind of neat, and we'll go ahead and work through this right now, is that when you take this, the gradient of this function called the Lagrangian, and you set it equal to 0, that's going to encapsulate all three equations that you need. And I'll show you what I mean by that. So let's just remember the gradient of L, that's a vector. It's got three different components. Since L has three different inputs, you're going to have the partial derivative of L with respect to x. You're going to have the partial derivative of L with respect to y. And then finally, the partial derivative of L with respect to lambda, our Lagrange multiplier, which we're considering an input to this function. And remember, whenever we write that a vector equals 0, really we mean the 0 vector. Often you'll see it in bold if it's in a textbook. But what we're really saying is we set those three different functions, the three different partial derivatives, all equal to 0. So this is just a nice, like, closed form, compact way of saying set all of its partial derivatives equal to 0. And let's go ahead and think about what those partial derivatives actually are. So this first one, the partial with respect to x, partial derivative of the Lagrangian with respect to x. It's kind of fun, you have all these curly symbols, the curly d, the curly l. It makes it look like you're doing some truly advanced math. But really it's just kind of artificial fanciness, right? But anyway, so we take the partial derivative with respect to x, and what that equals is, well, it's whatever the partial derivative of r with respect to x is, minus, and then lambda, from x's perspective, lambda just looks like a constant. So it's going to be lambda. And then this inside the parentheses, the partial derivative of that with respect to x, well, it's going to be whatever the partial derivative of b is with respect to x. But subtracting off that constant, that doesn't change the derivative. So this right here is the partial derivative of lambda with respect to x. Now, if you set that equal to 0, and I know I've kind of run out of room on the right here, but if you set that equal to 0, that's the same as just saying that the partial derivative of r with respect to x equals lambda times the partial derivative of b with respect to x. And if you think about what's going to happen when you unfold this property, that the gradient of r is proportional to the gradient of b, written up here, that's just the first portion of this, right? If we're setting the gradients equal, then the first component of that is to say that the partial derivative of r with respect to x is equal to lambda times the partial derivative of b with respect to x. And then if you do this for y, if we take the partial derivative of this Lagrangian function with respect to y, it's very similar, right? It's going to be, well, you just take the partial derivative of r with respect to y. In fact, it all looks just identical. Whatever r is, you take its partial derivative with respect to y, and then we subtract off lambda looks like a constant as far as y is concerned. And then that's multiplied by, well, what's the partial derivative of this term inside the parentheses with respect to y? Well, it's the partial of b with respect to y. And again, if you imagine setting that equal to 0, that's going to be the same as setting this partial derivative term equal to lambda times this partial derivative term, right? You kind of just bring one to the other side. So this second component of our Lagrangian equals 0 equation is just the second function that we've seen in a lot of these examples that we've been doing, where you set one of the gradient vectors proportional to the other one. And the only real difference here from stuff that we've seen already, and even then it's not that different, is that what happens when we take the partial derivative of this Lagrangian with respect to lambda, now I'll go ahead and give it that kind of green lambda color here. Well, when we take that partial derivative, if we kind of look up at the definition of the function, r never has a lambda in it, right? It's purely a function of x and y. So that looks just like a constant when we're differentiating with respect to lambda. So that's just going to be 0 when we take its partial derivative. And then this next component, b of xy minus b, all of that just looks like a constant as far as lambda is concerned, right? There's x's, there's y, there's this constant b, but none of these things have lambdas in them. So when we take the partial derivative with respect to lambda, this just looks like some big constant times lambda itself. So what we're going to get is, I guess we're subtracting off, right? It's up here kind of writing a minus sign. We're subtracting off all the stuff that was in those parentheses, b of xy minus b, that constant. And this whole thing, if we set that whole thing equal to 0, well, that's pretty much the same as setting b of xy minus b equal to 0. And that's really just the same as saying, hey, we're setting b of xy equal to that little b, right? Setting this partial derivative of the Lagrangian with respect to the Lagrange multiplier equal to 0 boils down to the constraint, right? The third equation that we need to solve. So in that way, setting the gradient of this Lagrangian function equal to 0 is just a very compact way of packaging three separate equations that we need to solve the constraint optimization problem. And I'll emphasize that in practice, if you actually see a function for r, for the thing that you're maximizing, and a function for the budget, it's much better, I think, to just directly think about these parallel gradients and kind of solve it from there. Because if you construct the Lagrangian and then compute its gradient, all you're really doing is repackaging it up only to unpackage it again. But the point of this, kind of the reason that this is a very useful construct, is that computers often have really fast ways of solving things like this, things like the gradient of some function equals 0. And the reason is because that's how you solve unconstrained maximization problems, right? This is very similar to as if we just looked at this function L out of context and were asked, hey, what is its maximum value? What are the critical points that it has? And you set its gradient equal to 0. So kind of the whole point of this Lagrangian is that it turns our constrained optimization problem involving r and b and this new made-up variable lambda into an unconstrained optimization problem where we're just setting the gradient of some function equal to 0. So computers can often do that really quickly. So if you just hand the computer this function, it will be able to find you an answer. Whereas, it's harder to say, hey, computer, I want you to think about when the gradients are parallel and also consider this constraint function. It's just kind of a cleaner way to package it all up. So with that, I'll see you next video where I'm going to talk about the significance of this lambda term, how it's not just a ghost variable, but it actually has a pretty nice interpretation for a given constraint problem.